Okay, I want you to just imagine for a second a computer so unfathomably powerful that it could solve the universe's most complex problems, and it's powered entirely by particles of light. Welcome to this incredibly exciting explainer where we're going to dive deep into one of the most cutting edge hardware races in quantum computing today.
Now, I know what you're thinking. It totally sounds like science fiction, right? But today, we are exploring how encoding information onto individual photons might actually solve the biggest bottlenecks we're seeing in the quantum industry. Photonic qubits use light as the fundamental unit of quantum information. And let me tell you, it completely flips how we traditionally think about building these massive, complex machines. So here is our roadmap for the explainer to demystify how these particles of light are accelerating toward real-world commercialization. We're going to cover 1. The quantum hardware landscape. 2. Meet the photonic qubit. 3. Computing by measuring. 4. Overcoming photon loss. And finally, 5. The commercial photonic market. Let's jump right in. Starting things off with Section 1, the quantum hardware landscape. When we look at the current hardware space, there is just a stark contrast between the leading approaches. Think about the highly popular superconducting qubits. They literally have to sit passively, frozen in place inside these massive, incredibly complex cryogenic fridges just to function. But photonic qubits, they're a whole different beast. They actively fly through circuits at the speed of light. And because photons have virtually zero environmental interaction, they naturally exhibit incredibly low decoherence. They basically just shrug off the thermal and magnetic noise that plagues those other stationary qubits, which makes them absolutely fantastic for communication. Moving right along to Section 2, meet the photonic qubit. So how do we actually put data onto a flying photon? Well, we have 3 brilliant ways to pull this off. First up, squeezed states. This is where we manipulate the actual rules of Heisenberg's uncertainty principle to quiet down the noise for specific phases, trading off noise in others. Then we have dual rail encoding, where a photon essentially chooses one of 2 physical paths, like a fork in the road, to act as our 0 or 1. And finally, Q modes, which use integrated optics and rely on quantum tunneling, allowing photons to pass between microscopic waveguides. Each of these gives us a unique, really powerful way to trap data inside a particle of light. And this brings us to their absolute superpower. Because these photonic qubits operate at the exact same telecom C-band wavelengths as our everyday internet traffic, which is around 1.55 micrometers, they can seamlessly connect diverse quantum modules, sensors, and memories over long distances. No massive frequency conversion hurdles needed. They are literally born ready for a quantum internet. But it begs the question, if these qubits are constantly zooming around at the speed of light, how on earth do they actually serve as a computing engine? Which brings us to Section 3, computing by measuring. The answer to that is a fascinating paradigm called measurement-based quantum computing, or MBQC. In this model, computation is executed by performing a highly specific sequence of measurements on a deeply entangled multi-qubit resource that we call a cluster state. So rather than trying to keep qubits alive and pristine for a long time like we do in superconducting circuits, photons are basically treated as expendable resources. We literally compute by consuming them. Think of it kind of like a continuous, ultra-fast manufacturing assembly line. Step 1. We rapidly produce the qubits in a qubit factory using sources like quantum dots. Step 2. We immediately stitch them together using linear optical components, things like interferometers and beam splitters, to build up that entangled cluster state. And then Step 3, we consume that cluster state via measurement. The outcome of one measurement actually dynamically dictates the basis for the next one, which drives the calculation forward at lightning speeds. It's incredibly elegant, but we do have to address the elephant in the room when it comes to working with light. And that brings us to Section 4. Overcoming photon loss. Because let's be real, photons easily get lost in the machinery. They just do. Traditional linear optical systems had to rely on this massive, resource-heavy, probabilistic redundancy to deal with lost light. If a gate only worked a tiny fraction of the time, you just run it millions of times with millions of extra photons. But new single-photon nonlinear architectures are a total game changer. They are replacing that massive overhead and making deterministic entangling gates a reality. By introducing photon-photon interactions, we can actually remove those old linear optical failure modes entirely. Instead of an optical setup the size of a warehouse, we can use these fault-tolerant base modules utilizing nonlinear seed state generators. They reliably and deterministically create the foundational entangled states needed for robust quantum computing, but without the staggering hardware footprint of older systems.
To show you exactly why this matters so much, just look at this number, 11.5%. By utilizing these new interactions alongside a 32-photon resource state, engineers have achieved a remarkably high baseline loss tolerance. That means that even if we lose over 10% of our photons to the environment or to imperfect detectors, the system can still flawlessly correct the errors and finish the computation. That is a huge breakthrough for practical scaling, and it's exactly why these architectural leaps are rapidly bringing photonic quantum computers onto the commercial horizon.
All right, let's wrap things up with Section 5, the commercial photonic market. To anchor all of this momentum with a hard number, consider QuICs. Their new integrated Omega chipset recently demonstrated an absolutely astonishing 99.98% single qubit state preparation and measurement fidelity. And that's alongside a 99.72% chip-to-chip interconnect fidelity. I mean, this hardware is legitimately reaching the stringent thresholds needed for fault-tolerant computation.
And that success brilliantly illustrates why the industry is so incredibly optimistic right now. As Professor Jeremy O'Brien put it, for more than 25 years, it has been my conviction that, in order for us to realize a useful quantum computer in my lifetime, we must find a way to fully leverage the unmatched capabilities of the semiconductor industry. That is the true power of photonic qubits, right there. They can be printed in massive volume using the exact same commercial silicon foundry processes that build the classical computer chips in your laptop today. So today, a really robust commercial market has emerged, primarily built around three distinct approaches. You've got continuous variable architectures from companies like Xanadu using squeezed optical fields. You have discrete variable chips from folks like QuICs and Orca Computing using individual photons. And then there are hybrid spin photon models from Photonic Inc., which literally link photonic networks to solid-state matter qubits. It's a thriving ecosystem, backed by a massive global supply chain of foundries and laser suppliers. Which leaves us with a truly electrifying final thought for this explainer. As semiconductor foundries begin to churn out millions and millions of these microscopic optical circuits, will the world's first true quantum supercomputer simply be a web of light coursing through our existing telecom infrastructure? I mean, are we standing on the precipice of a future where quantum computing is completely and seamlessly integrated into the very fiber optic light that already connects our world? What an amazing space to watch. Thank you so much for joining me to explore this fascinating source material today.